Hi there, my name is Michael Harding. Thank you for tuning in to my Workshop 2 presentation. To get us started here, what I'd like to do is review the problem just a little bit. So what we have is we are given a matrix and a desired integer value set to v. What we need to do is we need to determine if there are any square submatrices whose total value is equal to that given integer value v. These submatrices can be any size between 1 by 1 all the way up to the minimum the minimum dimension of our matrix, which we're going to set to k. I'll show you shortly. But any submatrix between the sizes of 1 by 1 all the way up to n by n, or the minimum dimension of the given k of the given matrix. And again, all of these submatrices are square. So Dr. Spradling was kind enough to give us a brute force algorithm to get us started. I'd like to review that just a little bit. I'll talk about it and then show it. It starts by establishing the current size of the submatrix, and then from there, it iterates through all of the submatrices of that size. When all of the submatrices of that size are exhausted, we iterate the size, and we check all of the possible submatrices of this new size, starting again from our beginning coordinates of 0, 0. I'll show it to you now. This would be Dr. Spradling original. As you can see here, we're gonna set our integer values, and we are going to use these first, or this first for loop to iterate the size of the submatrix we're checking. And here, what we're doing is we are iterating through our starting coordinates for our matrix. And then our innermost loops here are for iterating through the submatrix and adding those values to the sum. Now, as you can see here, the time complexity for this brute force is going to be big O of n to the fifth. This is because those first three loops run together in big O of n cubed time, where n is equivalent to the size of my matrix. And the last two loops run in big O of n squared time, because they iterate over all of the rows and columns of the submatrix. Now, excuse me, we can say that because the big O of n squared inner loops are run big O of n cubed times. So we have an overall time complexity big O of n cubed, or I'm not sorry, I'm big O of n to the fifth. In terms of space complexity here, the only real relevant allocation of storage here is going to be the initialization of the vectors that store my matrix. Check matrix function itself, it only initializes a few variables which require constant space. I'll show you those again. They were our initial values here is the x, y, k sum is in addition to the cur size, I, j, m, and n. They're all constant values, so we can disregard them to a degree. Now I'd like to explain my code a little bit, and then we'll take a look. My code, it starts by establishing the starting coordinates of the submatrix. So whereas in the last code we started by setting the submatrix size, we're going to start with coordinates here. So we'll do x and y coordinate followed by setting the size for the submatrix. So once we have our coordinates, we're going to use a for loop. Or using a for loop, we establish how the submatrices will increase in size from the starting coordinates. So that first 1 by 1 matrix, we will place the corresponding value right into the sum variable and compare it to v. Without resetting the sum, what we'll do is we'll iterate the size of the submatrix and use a path with two separate loops, which add the new values of the submatrix to the existing sum of the previous submatrix. The sum will only reset upon changing the starting coordinates, which happens after exhausting all of the submatrix sizes for those specific coordinates. So let's take a look here, and I'll try to explain it again. So what we do is very similar to how we start the Dr. Spradling original code. We have the x, y, pay and sum here. From there, what we will do is we'll jump right into moving our coordinates around. So we'll start here at 0, 0, as you can see. And then our next loop inside is going to be manipulating the size of our current submatrix. So we're at 0, 0. Our current size is 1. So what we'll do is we'll drop into this chunk of code here. What it'll do is it will literally read whatever that ij, that 0, 0, my matrix 0, 0 reads right into the sum without any hesitation, and then compares it to v. From that point, what we will do is jump back around, iterate the size. So now we're at a 2 by 2 matrix. And what we will do is we will, because we haven't reset the sum yet, so our sum still contains that 1 by 1 matrix. We will skip this 1 by 1 because obviously we're larger than 1 at this point. And we will jump into iterating across the very bottom of this submatrix. So for reference, what I'm talking about is here's our first loop, and it reads that 0 in. Then we're going to increase the size of the submatrix to read these four values here. So what we'll do is we'll start here with this first loop and move across. So we'll add this value and this value to the pre-existing sum. That's what this first separate for loop does. Then from there, what we're going to do is we're going to ignore that bottom right-hand corner. We're just going to add the right-hand side that doesn't include that bottom right-hand corner. And after that loop is complete, that will give us the entirety of that 2 by 2 matrix. So we are going to compare it to V. It fails, then we will hop back here. This line of code is finished, so we hop down here, ride up, increase the size. So now we're looking at a 3 by 3, and we haven't reset our sum value yet. So if we're looking at the 3 by 3, we will already have these 4 values put in sum, and we're going to start here at this too. So we'll add this in our first loop. We'll add this in our first loop. We'll add this in our first loop down there. And now from here, we jump to our second loop, which is going to read this and this. It disregards that bottom right-hand corner, so it doesn't get counted twice. And you can see that it does that right here by setting it just one higher than the maximum of the submatrice. So with that being said, let's take a look at proving it before I move into the time and space complexity. I'll try to hop back and forth here so you guys can see the code too. Well, actually, why don't I do that first? Let's take a look at what loop I'm talking about. We're talking about this first loop here, which is going to iterate our x. This is going to iterate our x starting coordinate across the my matrix. So before entering our outer loop here, the sum would equal 0, as we haven't checked any values yet, and therefore that 0 would be correct. To maintain this specific loop, in loop 2 that we're going to look at next, loop 2 exhausts the entire column, and then at that point is when we would iterate this loop 1. So at this time, the sum would again be reset to 0, and that would be maintaining its correctness. Every time our next loop iterates, it'll I'm sorry, every time that we come to this this loop, all it does is changes the x coordinate. And it's important to keep in mind that every time we change a coordinate, we will be resetting our sum to 0. So before every iteration of this outer loop, the sum would be reset to 0, and this ensures the correctness. Termination. So for terminating this loop, after exhausting all of the matrix rows in our program, which is what this particular loop does, we will either get a return true or false, or sum will be zero. Depending on the given value, either of these would be correct, and therefore the correctness is again it maintained. So I touched on it a little bit, but loop 2 here is simply our y correspondent. It's right here. This iterates down the matrix as opposed to across it like the first loop. So for this particular loop, similar to the previous, before the first iteration, we will have not checked any values yet, and our sum would be equal to 0, which obviously is correct. But here's where it gets a little bit goofy. The first order of business for this particular loop is to set the sum to 0. So before our first iteration, obviously it's at 0. We haven't checked anything yet. But after we iterate for our first time through, we will have a sum at that point. So when we return to iterate here, before we iterate again, sum will contain the value of the previous submatrix, or the current submatrix if we haven't iterated yet, if that makes sense. So after exhausting all of the submatrices, using the following code, the next loops, this is where the loop would iterate. At this time, the sum would have a value of the last submatrix checked, like I just said. This maintains our correctness because the first order of business in the loop is to reset the sum, and before every iteration, we will always find the sum of the previous submatrix, even if that's 0, like we haven't checked anything yet. For terminating the second loop, this exhausts all of our matrix columns. Once that happens, our program will move to ensure that all the rows are also exhausted before returning true or false. This maintains our correctness. As we exhaust our columns, we will either change the coordinate of the rows, or we will be completed. Obviously, when we are completed, our code will either return a true or false, depending on our given. So now for this third loop here, I'll show you the code. This is our technically like the first line of code in our Dr. Spradling original brute force. Here what we're doing is we're manipulating the current size of the submatrix. Obviously, we're starting out 1 by 1 here, and we're moving up to k, which is set to our minimum dimension. And we will iterate this to its fullest extent possible before resetting the sum to 0. This is going to allow us to make less additions to the sum, as we aren't double counting nearly as many coordinate positions. So again, we're going to be talking about the cur size loop here. So before our first iteration, the sum is 0, as we still haven't checked any values yet, and therefore this would be correct. Now, as we iterate this loop, whenever we need to increase the size of our submatrix, our sum will contain the previous submatrix, so that we're not doing as many additions. And every time we want to iterate this loop, every time we go to iterate this loop, the sum variable will contain the previous submatrix sum, and this would be correct at this point. After exhausting all of the possible submatrices for all of the possible starting coordinates of our program, it'll either return true or false, and this is maintaining our correctness as well. So now let's look at our loop 4 here. This is going to be all the way down here in our little else pathway. Now, what happens here is the first, the 1 by 1 matrix gets weeded out, and we have it put into the sum here. We compare it, obviously, but we'll come down, and this is for where we begin our 2 by 2 and greater submatrices. Our first loop here that I'm talking about is only going to be pertaining to that bottom row of the new submatrix, or not new, but current submatrix. So if we're looking at a 2 by 2 here, I'm talking about these two values. Now, before the first iteration of this loop, we will have already checked the value that corresponds to the starting coordinates of the matrix and stored that value in sum. Now, this would be correct. So that is basically saying that before we even touch this loop, the for loop right before it has iterated, and sum is occupied by whatever that 1 by 1 matrix was. Now, as we iterate on this loop, to move across the new lower row of the current submatrix. And before iterating, the sum variable will contain all of the checked values up to that point, which maintains the correctness. So when we go to start our third iteration, when we're looking at 3 by 3 submatrices, the sum value will contain the 2 by 2 submatrice. Upon the termination of this loop, we will have added all of the values along the bottom of the submatrix to the sum variable, and that would be correct at this point. So now what we're going to do is we're going to look at our last loop here, which is shown right here. This is for that right-hand side of the submatrix. And so for a 2 by 2, I'm referring to only this. And for a 3 by 3, I'm referring to only these two, because we have already taken care of that bottom right-hand coordinate in our first of the two for loops. So with that in mind, let's take a look here. For initialization of this particular loop, before the first iteration of this loop, the sum variable will contain the previous submatrix sum, as well as the entire bottom row of that current submatrix. This would maintain our correctness. Now, for maintaining this loop, we iterate on this loop to move up the far right-hand side of the column, or right-hand column of the current submatrix, as I stated before. Now, before iterating, the sum variable will contain all of the checked values in the current submatrix up to that point, which maintains our correctness. So if this is a 3 by 3 we're looking at, sum will contain the 2 by 2 matrix, as well as the bottom three the bottom three values of our 3 by 3 matrix. Now, upon termination of our loop, we will have successfully added all of the values that correspond with the new layer of submatrix to the previous, giving us a correct total for the current submatrix. As this happens for every submatrix size, for all starting coordinates of the matrix, we can be confident that this program maintains its correctness. So now we'll take a look at time complexity. The Dr. Spradling original was able to pull off the feat in big O of n to the 5th time. And this is because there are big O of n squared is being run big O of n cubed times. So now let's head back to the program here, and if I can scroll over, we'll take a look. So our first chunk here is very similar to Dr. Spradlings, where we've got the big O of n cubed, and this is due to x times y times k. It gets that first part done, this first part right here. For our first 3 loops, and then down at the bottom here, we've got our a total of big O of 2n, which simplifies to big O of n. Now, this is due to the for loops being run separately but not nested. So this particular n would run n 3 times, or n to the 3 times. Let's head back to my slides here. I believe I have managed to say a lot of this, but here we managed to complete it in a total time complexity of big O of n to the 4. Uh, yeah, big O of n to the 4. Um, our first three loops, like I said, our first three loops are very similar to Dr. Spradling's brute force. Just a little reordering occurred because I decided to move that manipulating the current size of the submatrix to after the coordinates, where it was opposite there in the brute force. And the last two loops, excuse me, are nested um, in the original three, but are separate from each other. They're not nested inside of each other. This allows us to have a time complexity of n plus n for that portion, as opposed to n times n like in Dr. Spradlings. Now this leaves the last two loops with a time complexity of big O of 2n, which simplifies to big O of n. Now from here we can combine under the idea that the last two loops, big O n, are run big O n to big O n cubed times. So simply put, we have big O n to the 4th. In terms of space complexity, my code is actually equivalent to the Dr. Spradling original in terms of space complexity. The only thing that is real relevant here is the initialization of the vectors to store my matrix. That's done in big O of n squared, or I'm sorry, n cubed. Oh, wow, n squared time. Wow, this is done in big O of n squared space. The check matrix function only initializes the variables x, y, k, sum, I, j, cur, size, m, and n, which are alt constant space, so they can be disregarded to some degree, which leaves us with a total space complexity of big O of n squared, which again is equivalent. Yeah. And lastly, I'd just like to thank you for listening in. I hope you enjoyed it. I hope it was educational. Good luck with your own workshops. And then quick shout out to Dr. Spradling. Thank you for the brute force code. It really helped me get on the right track. Um, Much appreciated. Thanks again for tuning in. I hope you enjoyed.